Okay, let's get into this. We're looking at a concept that is, it's truly audacious.
It really is.
It sits right at the intersection of AI, energy, orbital mechanics. We're talking about moving the entire infrastructure for training the world's biggest AI models.
Thousands of GPUs.
Exactly. Thousands of them, not just to a new data center, but into low Earth orbit.
You know, it sounds like a premise ripped straight from a sci-fi movie, but the research we've been looking at, especially these architectural papers from Google,
Right.
they show this is moving very quickly from, a fantastical idea to what might be an inevitable economic necessity.
Absolutely. And the source material, it frames this orbital move not as some, hopeful future thing, but as an urgent escape.
An escape from a crisis that's happening right now.
Yes, what they've called the terrestrial bottleneck.
Mhm.
Down here on Earth, data centers are just slamming into physical limits. We're running out of power. We're running out of water for cooling.
And we are definitely running out of patience with zoning boards. I mean, you just have to look at places like Northern Virginia to see that.
So the core conflict is, it's simple, but it's relentless. The demand for generative AI compute is scaling exponentially.
I mean, we're doubling complexity every few months, but the energy grids we rely on, they grow linearly at best.
So this whole infrastructure shift, this exodus to orbit, is designed to completely sever that AI scaling curve from Earth's finite resources.
That's the goal.
So our mission in this exploration is to really dissect if this plan is viable. We're going to analyze the specifics from, say, the Google designs and look at industry moves like what Starcloud is doing.
Right, to see if the physics actually holds up.
And the engineering, and most critically, if the economics work. We're focusing on a massive capital-intensive infrastructure play here. This shifts the conversation away from general goals like space exploration.
It centers entirely on the hard numbers, on FLOPS.
Floating point operations per second.
And that focus on raw compute, it leads to two critical design assumptions that are, well, they're literally impossible to achieve at scale on Earth.
Okay.
The viability of this whole model rests on, one, access to essentially infinite solar energy, and two, the possibility of near absolute zero cooling. If you can unlock those, the prohibitive costs of doing this on Earth just vanish.
Let's start right there then with the main motivation. Power. Data center power use is starting to rival that of small nations. It's not about just buying the latest Nvidia chip anymore. It's about feeding it the gigawatts it needs. Can you paint a clearer picture of that gridlock?
The power thirst is just staggering.
Yeah.
We're already seeing major tech companies forced to become, in effect, their own utility providers.
Right.
Google, for instance, they've had to invest heavily in their own power sources, things like geothermal, even looking at small-scale nuclear.
Just to keep the lights on for their big models.
Just to make sure that operations running things like Gemini don't crash the regional grid. And even if you solve the power in, you still have the heat out. Every one of those gigawatts becomes waste heat that has to go somewhere.
So we're in this feedback loop. Scaling compute means scaling resource use, and Earth just can't keep up at this exponential rate. So the solution to just leave the grid behind entirely.
That is the elegant core principle. The sources highlight some pretty dramatic numbers. The sun outputs 3.86 times 10 to the 26 watts.
Which is an enormous number.
It's 100 trillion times more energy than all of humanity currently produces. And when you put your hardware in orbit, you bypass two huge efficiency filters. The atmosphere, which absorbs energy, and, well, night.
And that orbital position isn't just a small boost. It sounds like a total economic transformation.
It truly is. Because you eliminate the atmosphere and you reduce the day-night cycles, a solar panel in space can receive up to 8 times more energy per year than the exact same panel down here on Earth.
8 times, 800% more efficient.
When you can generate energy that efficiently, the entire cost calculation just flips on its head.
That 8-fold increase is the engine driving this whole concept. So the race for compute, it's not about land near a hydroelectric dam anymore.
Correct. The competition shifts from, flags and footprints to FLOPS. The bottleneck is no longer fighting bureaucracy or grid capacity on Earth. The bottleneck simplifies to just one thing: launch mass. How much stuff can you affordably get into orbit?
Okay. The economics clearly point up, but the skeptics, they'll immediately pivot to the engineering. How do you actually operate a massive supercomputer 600 kilometers above us? What are the big hurdles? We need power, cooling, and connectivity.
And the most critical choice that impacts all three of those is the orbit itself. The specific orbit dictates everything.
Which brings us to this Goldilocks zone from the research. the dawn-dusk Sun-Synchronous Orbit, or SSO. Why that specific path?
It's a brilliant solution to a weight problem. In a dawn-dusk SSO, the satellite is engineered to constantly ride the terminator line.
The edge between day and night.
Exactly. It stays in perpetual sunlight, 24/7. This completely eliminates the single heaviest non-payload item on most satellites, the massive batteries you need to survive the dark side of the planet.
So getting rid of a few tons of batteries saves a ton on launch costs and frees up that mass for more valuable compute hardware.
Okay, you have continuous power. What about the network? How do you link 81 separate satellites so they act like one?
Well, you can't use fiber optics. In space, you use free space optical intersatellite links, FSO.
So lasers.
High-powered lasers, yeah. And here's where the physics of a vacuum becomes a huge advantage. Light travels roughly 31% slower in glass fiber than it does through empty space.
31%. That's an enormous speed advantage for inter-chip latency.
It adds up incredibly fast. The Google architecture imagines this tightly controlled swarm of 81 satellites in a cluster just 1 kilometer across. By keeping them that close and using FSO, they can use a technique called spatial multiplexing to hit massive aggregate bandwidths.
How massive? 10 terabits per second. That's what lets the whole orbital cluster function as a single, tightly coupled supercomputer.
That is astonishing. Okay, now let's tackle the physical objections. The first one you always hear is cooling. The Thermo 101 objection. Space is cold, but there's no air. The chips will melt. How do you get around that?
It's true. A vacuum is a fantastic insulator, so convection blowing air is useless.
Yep.
But what you gain is a perfect environment for radiative cooling.
Okay.
Everything emits heat as infrared radiation. The rate scales with the fourth power of its temperature. You don't need a fan. You just need a really cold place to point your radiator.
And that ultimate cold sink is?
Deep space. Google's design uses heat pipes to move thermal energy away from the hot chips to large radiator panels. And those panels have to be pointed exclusively at deep space, which is only about 3 Kelvin.
Negative 270 degrees Celsius.
Right.
But cooling isn't really free then, is it? It costs way. You're trading a fan for a massive radiator that can never, ever point at the sun or the earth.
That's the critical engineering trade-off. You pay for cooling in mass and in control systems. But we know this works. The James Webb Space Telescope is the ultimate example of passive radiation cooling. If we can cool a sensitive scientific instrument, we can cool a TPU chip.
All right, that handles the slow killer, heat, now the sniper threat,
Yeah.
radiation, cosmic rays, high-energy protons. How do you stop a single particle from causing silent data corruption and ruining a 3-month training run?
This is probably the most serious threat to the mission. To figure this out, Google did a pretty detailed test. They took their Trillium TPU chips and blasted them with a 67 MeV proton beam.
To simulate a LEO environment.
To simulate the cumulative dose of a 5-year LEO mission, yeah.
And did the hardware survive?
The results were surprisingly robust. The logic cores of the chip survived the whole simulated mission with just standard shielding. We're talking about 10 millimeters of aluminum.
That's it?
That's it. But the weak point, the most vulnerable part, was the high bandwidth memory, the HBM. It's just so dense, it's a bigger target.
So you can't stop the radiation, and you can't build heavy lead walls because that would kill the economic model. So the solution has to be digital.
It's all about software resilience. The data showed uncorrectable errors in the HBM at a rate of about 1 per 50 rads. So instead of heavy shielding, you rely on robust error, correcting codes, ECC, to fix bit flips on the fly. And, crucially, checkpointing.
Constantly saving your progress.
Exactly. The system just assumes failure is guaranteed. So if an uncorrectable error happens, you just rewind a few seconds instead of scrapping the whole multi-month run.
Okay, so the physics holds up, the engineering challenges are solvable, but none of that matters if it costs a fortune to get it all up there. We have to talk about the economics.
This is where it all comes together. The entire feasibility of this hinges on one single metric, the launch cost per kilogram. If that number doesn't hit a specific target, this is all just a fascinating thought experiment.
And historically, launching cargo has been, well, astronomically expensive, upwards of $30,000 a kilogram in the shuttle era. So what's the magic number? What's the target to make orbital AI cheaper than terrestrial AI?
The target cost is a staggering $200 per kilogram.
200.
200. That's a greater than 99% cost reduction from historical norms.
That seems incredibly aspirational, even for something like Starship. What if they miss that target? What if it settles at, say, $800 per kilogram? Does the whole thing just fall apart?
Well, at $800, the economics definitely get tighter, but the model doesn't immediately collapse. The $200 figure, though, is the sweet spot. That's the point where the initial cost for the power capacity becomes directly competitive with building it on the ground.
How so?
Google's analysis found that at $200 a kilo, the launched power price, the cost to put 1 kilowatt of generating capacity into orbit drops to roughly $810 per kilowatt.
And if you compare that $810 per kilowatt of building a terrestrial data center, that can range from, what, $570 to $3,000 per kilowatt?
Exactly. So space becomes highly competitive right out of the gate. And that's before you factor in the operational savings. Once it's up there, the utility bill, the biggest recurring cost for any data center on Earth, goes to zero. The energy is free forever.
So you're trading a massive recurring OPEX for a colossal but one-time CapEx.
Which is why SpaceX and vehicle reuse is the fundamental variable that underpins this entire premise.
Right. Now let's address the elephant in the room that always trips people up, latency. Why would anyone want their AI to lag? Because the signal has to go 600 kilometers up and 600 kilometers back down.
That skepticism comes from a fundamental confusion about the workload. This isn't for your phone's voice assistant. It's optimized entirely for the training phase, not inference.
The inference being the real-time interaction.
Right. Training is the killer app here.
Training, as in the months-long process of building a huge model like GPT-5 or a new Gemini.
Precisely. That takes months of continuous processing, massive power, and huge interchip bandwidth, which those 10-terabit laser links provide. The latency to Earth during that crunching phase is completely irrelevant.
So the workflow is, you upload the data, let it cook for a few months, and then download the answer.
Pretty much. You upload the huge training dataset once. The satellites crunch the numbers for 3, maybe 6 months. Then when it's done, you beam down the resulting model weight file, which is actually pretty small. The whole thing is just a self-contained supercomputer in a vacuum.
A dedicated off-planet factory for creating foundation models. So while Google is writing the papers and testing the chips, who's actually putting hardware in orbit? Who are the first movers?
The startup Starcloud has been the most visible. They hit a huge milestone by launching a commercial-grade Nvidia H100 GPU into orbit.
The crucial proof of concept.
Yeah, proving that standard commercial hardware can survive the launch and operate in that thermal environment.
And I've got to imagine that got Nvidia's attention.
Oh, absolutely. The demand for ruggedized, radiation-tolerant chips that still have cutting-edge performance basically forced Nvidia to create a whole new product vertical. We're seeing the rise of Space H100s, with enhanced resilience baked right in.
And what about the big hyperscalers, the primary customers?
Well, you have Google, who is clearly focused on the architecture and their own custom silicon. And then you have Amazon and AWS, who are in a perfect position for vertical integration.
They have Blue Origin for launch.
And initiatives like Project Leo, which signals their intent to extend the AWS cloud platform directly into orbit.
But whether it's Google, Amazon, or a startup, we keep coming back to the same enabling factor.
That's right. SpaceX is the fundamental variable in this whole equation. The entire competitive landscape depends on them hitting that $200 per kilogram target. Without that, the economic argument just fails.
So this analysis of the source material, it really strips away the sci-fi and grounds this in some brutal economic logic. The physics works. The logic of escaping Earth's energy bottleneck works. But the whole thing, it hinges on Starship achieving that single game-changing price target.
If that cost collapses, gravity truly loses its grip on our digital infrastructure. We are witnessing the very early stages of building a planetary-scale computer. And it just so happens its motherboard is going to be floating 600 kilometers above our heads.
It seems like the cloud was the right metaphor all along. We were just aiming a little too low.
You know, this raises an important question for you to think about, based on everything we've looked at. If the primary energy source and the physical location for training the world's most powerful AI systems move outside of national boundaries, what happens to the global distribution of digital power? Will access to the highest level of AI capability become solely the domain of those who control the infrastructure of low Earth orbit? The resource race for the future of computation may have just shifted its axis entirely.